What we want to talk about now are what we call aqueous reactions. Those are simply chemical reactions that are done in water and solution stoichiometry. And since we're doing stoichiometry of solutions, we're going to be doing some calculating, some measurement of the elements, as it were. And so what we'll start out with are acids. You've heard the word acid for a very long time in your life. Let's see what an acid is. And I might start out saying that there is more than one definition of what an acid is. We're going to deal with one specific definition called the Arrhenius definition of an acid. And so here we go. So an acid is a substance that donates hydrogen ion to an aqueous solution. So here is our generic acid. We're simply going to call it HA. You're easily going to be able to recognize acids because they start with H in this domain. And so anytime you see a molecular compound that has an H on the front end of it, that is probably going to be an acid. And when you put it in water, it donates a hydrogen ion, which is simply a proton, to water. And I'll talk a little bit later about exactly what that means and what the chemistry is of that. And you also have an ion that was associated with this molecular compound that we're calling an acid. So an acid will donate two components to water. It'll be a hydrogen ion and the anion associated with that compound. What we call a base in this context is going to be some metal and this guy right here. And this is hydroxide ion. You remember hydroxide from your list of polyatomic anions. And what bases will do is they will donate that hydroxide ion in water. You will also have a metal cation floating around in that solution. And one of the things that you'll notice referencing the last video is that both acids and bases put ions into solution. That makes both acids and bases electrolytes. And they're electrolytes because they put ions in solution. All right, so if I do a reaction with an acid and a base, I'm going to get two products out of that. One of those products is going to be water from combining the hydrogen ion with the hydroxide ion. That's going to make water. That'll be what we call the driving force for that reaction. But the other substance that comes out of that is a metal cation with an anion. And so that's just an ionic compound, and with an acid-base reaction, we call that a salt. So that's going to give us our salt, and that our salt is just the result of an acid-base reaction that produces water, and here is the ionic compound, the salt. If you remove the water, you'll have a solid. But with this substance in water, these two ions will typically, not in every single case, but typically remain dissociated. And this is also making this usually an electrolyte. Remember, anytime you have ions in solution, you've got yourself an electrolyte. Okay, so let's go a little bit deeper. So acids, substances that ionize to form a hydrogen ion. H plus is a hydrogen ion. Acids increase the concentration of H plus, and we call them proton donors because if you think about it, if hydrogen is a proton and an electron, and you take away the electron, all you have left is that positively charged proton. And so we call acids proton donors. Okay? Acids decrease the concentration of hydroxide ion. Well, how do they decrease the concentration of hydroxide ion? Well, if I have hydroxide ion in solution and I add an acid, these two guys are going to be very interested in each other, and they're going to get together and they're going to make water. So they actually decrease each other's concentration by combining to form water. So protic, this prefix we say protic, it just means protons, the number of protons. And so if I say monoprotic, well, you know that mono is the prefix for one. That just means there's one H plus per molecule of acid, and that would be something like HCl. For every one molecule of acid, there is a single proton to donate, and that would make that a monoprotic acid. And then we could have a diprotic acid. It yields 2 protons per molecule of acid. And so for a diprotic acid, that would be something like H2SO4. Notice that for every one molecule of H2SO4, there are 2 protons that can be donated to the solution. And then a triprotic acid would simply be 3 protons per mole of acid or molecule of acid. So that would be something like phosphoric acid, H3PO4. And all I'm looking at for a triprotic acid is the subscript to the right of the H that says 3. This is a triprotic acid. H2SO4, this is sulfuric acid. It's a diprotic acid. And then HCl, HBr, HNO3, those are all monoprotic acids, so it's a 1 proton per molecule of acid. All right, so that's all mono, di, and triprotic mean. We have what we call strong acids. And strong acids are strong electrolytes. And what that means is they ionize pretty much relatively completely in dilute solutions. Okay, they ionize completely. So strong acids put lots of ions in solution. That means that strong acids are strong electrolytes. So you're going to need to know the name of all 7 of these strong acids. This is hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric. There's your only diprotic acid on the list. This is chloric and perchloric acid. I'm going to show you how to determine what those names are, but if it were me, I would stop the video right now. I'd spend about 3 or 4 minutes learning the formula and the name for each of those 7 strong acids. Just kind of get yourself started on that road, and then the rest will be easy. Well, why do we need to know the 7 strong acids? Well, because you need to be able to recognize the weak acids. And the weak acids are every other acid that you're going to encounter in this course other than these 7 strong acids. Now, remember that the acids in here will always start with H. There'll be some anion here. But if it starts with H, we're calling it an acid. If it's a weak acid, it only ionizes a little bit. And we're always doing, this is aqueous chemistry we're doing. So I get just a little bit of concentration of ions, hydrogen ions in solution. So these only partially ionize, whereas a strong acid pretty much completely ionizes in solution. So classify acids as weak or strong acids. Well, that's really going to be easy. All you have to do is back up the video or look at your PowerPoint notes. Here are your 7 strong acids. Every other kind of acid is a weak acid and a weak electrolyte, by the way. And so HF, this is hydrofluoric acid. It's not on the list of strong acid, so that means it's a weak acid. Now, I'm going to just use some abbreviations. If I mean weak acid, I'm just going to say WA, and that just means weak acid. This is sulfuric acid. It's a diprotic acid. It is on the list of strong acids, so this is a strong acid. Now, what does it mean to say an acid is strong? It means it completely dissociates or ionizes, which is more appropriate since these are molecular compounds. It completely ionizes in solution. Well, HF is a weak acid, so I'm going to give you a choice. I've got what we call concentrated hydrofluoric acid and concentrated sulfuric acid. This is battery acid. You find this in the batteries of car batteries. It's the electrolyte for car batteries. HF, hydrofluoric acid, it will etch glass, but it is a weak acid. So which one do you think I would rather have spilled on me? Sulfuric or hydrofluoric? Sulfuric is strong, hydrofluoric is weak. It's an interesting question. And the answer is I would actually rather have this strong acid. Neither one's going to be a pleasant experience. Sulfuric is going to burn me. It's going to hurt like hell. I've never actually had a major acid spill on my skin. I've had some small acid spills on my skin. But hydrofluoric can be very deadly stuff. So I want you to go to the internet. You can just go to Wikipedia for hydrofluoric acid, HF. Take a look. Okay, do a little bit of homework on hydrofluoric acid and sulfuric acid, and you'll learn why I would rather have sulfuric dumped on me than hydrofluoric dumped on me. Neither one's great. So anyway, we've got weak and strong. So B would be our answer. So before I show you the strong versus weak acid animation, I want to show you something. So here we go. So here is an acid, and I'm just going to use the generic HA. This could be any anion, and we know it's an acid because it starts with H. And I'm going to put it in water. So I'm going to add this to H2O. Now, first, well, let's do it this way. Okay. So when I add my acid to H2O, here's what happens. The H2O is going to accept that proton, and it's going to form an ion, a molecular ion called hydronium ion. This is the hydronium ion. And of course, we'll have the A- anion floating around in here. So let me show you what that actually looks like. You've got HA. Here's what the water molecule looks like. There are actually two non-bonding pairs of electrons. Remember, this is a very polar molecule. This end of the molecule is partially negative. This end of the molecule is partially positive. The acid is also a very polar molecule, and the positive charge is here, the negative charge is over here. So when you add the acid to the water, these electrons are going to reach out, so to speak, and they love the positive charge on this proton, and so what you're going to wind up with is the hydronium ion, which looks something like this, and there's still a non-bonding pair of electrons on here. This is also a representation of the hydronium ion. It is a drawing of that polyatomic cation, the hydronium ion, and then of course and it's got a positive charge, and then you're going to have the anion sitting out here. Now, we usually, when we write these reactions, normally just assume the water is there. We're assuming water is here, whether we write it or not, and we just say H plus plus A minus. When a more accurate statement is to actually put the water as one of your reactants, because it's going to accept the proton from the acid and make the hydronium ion. And even more accurate would be to draw the Lewis structure here, draw the Lewis structure for water, and show that the water molecule, the oxygen in the water molecule, is going to accept that proton to make the hydronium ion. So that's even more accurate. But, you know, most of the time we just do this when what we mean is that or that. And they all represent the same thing. When we do it this way, we'll just call this the hydrogen ion. Hydrogen. There's an O in there, hydrogen ion. But remember that when we say hydrogen ion, what we really mean in water is the hydronium ion. So that's a hydrated hydrogen ion. We call it either the hydrogen ion or the hydronium ion. This is, when we call it a hydrogen ion, we're just understanding that water is part of the reaction. Okay? All right, so let's take a look at the strong versus weak acid animation.
The strength of an acid refers to the extent that it dissociates into ions when dissolved in water. Strong acids dissociate nearly completely. Weak acids dissociate very slightly. Dissociation into ions means that when an acid, HA, dissolves in water, it transfers a proton to one of the water's lone electron pairs, and the acid anion, A-, and a hydronium ion, H3O+, form. The color change of the water oxygen will make it easier to follow in solution later. The key difference between strong and weak acid dissociation is the final concentration of hydronium ion in solution. Since proton transfer from a strong acid to water is nearly complete, the hydronium ion concentration is essentially the same as the original acid concentration. In contrast, proton transfer from a weak acid to water becomes balanced by proton transfer from hydronium ion to A-. So the final hydronium ion concentration is much less than the original acid concentration. Let's view acid dissociation at the molecular level and focus first on strong acids. The concentrated acid in the beaker consists primarily of acid molecules. As soon as they make contact with the water in the flask, proton transfer from HA to H2O occurs for virtually every acid molecule. Note the change from blue to red. Therefore, a strong acid solution consists of hydronium and A- ions in water and virtually no HA. It follows that the acid dissociation constant Ka for a strong acid is very large. Now the beaker contains a weak acid. As before, the moment the acid molecules make contact with the water, proton transfer from HA to H2O occurs. But in a very short time, proton transfer from hydronium ion to A- balances it, and equilibrium is reached. Thus, a weak acid solution has a relatively high concentration of HA and very low concentrations of H3O+ and A-. Therefore, the acid dissociation constant is very small.
All you have to remember about weak acid is that they only partially ionize in solution. Okay? They only partially ionize in solution. All right. So nomenclature. We need to learn how to name acids, simple anions. This is a review. Remember, if it's a binary compound, it gets an IDE ending. So the IDE just indicates a binary compound composed of only two elements. We had sodium chloride And then we had potassium fluoride. Those are two binary compounds that end in IDE. For oxyanions, those containing oxygen, we started out with the ATE. If we went to one less oxygen, we went to ITE, and then one more less. One fewer oxygens, we went to hypoite. And then if we added an oxygen to the ATE, we went to per-ate. So that's just a review of what we did in Chapter 2 with regard to naming ionic compounds with polyatomic anions. All right, so we're going to apply that to our acids and what we call acid nomenclature. If you have a binary acid like HCl, we're going to, it's got an ide, so HCl is hydrogen chloride. We're going to add a prefix, hydro, then say the anion name, and then add the suffix ic and the word acid. Ates, you don't have any prefix for just a straight Ates anion. You just say the name of the anion, add the suffix ic, and then the word acid. If it's an ITE ending, you don't have any prefixes. You just go straight to OUS and then the word acid. So here we go. Acids from binary compounds, IDE endings, like HCl, hydrogen chloride. Drop the ide, add the prefix hydro, the suffix ic, and the word acid. So HCl becomes hydrochloric acid. Prefix hydro, chloric acid. You just get rid of the IDE, add ic, and then acid at the end, okay? So that's for binary acids. Acid nomenclature. Acids from compounds with polyatomic anions ending in ATE, like hydrogen phosphate. Just drop the 8, say the polyatomic anion name, add the suffix ic and the word acid. So hydrogen phosphate simply becomes phosphoric acid, which is H3PO4. It's a triprotic acid, and it's a weak acid, by the way. It's not one of your strong acids. A lot of people make that mistake. What about hydrogen phosphite? That's going to be H3PO3. Well, you've got an ITE, so you drop the ITE, you add the suffix us, OUS, and then the word acid, so this becomes phosphorus acid. Let's do a little bit of practice, all right? So I'll give you just a moment with each one. This is phosphate. We just did this one. Drop the ATE, say the anion name, add ic, acid. So this would be phosphoric acid. Yeah, we did kind of squeeze an O in on that one. No, nothing's perfect. Here we have acetate. This is an ATE, so acetic is the way we pronounce that, acid. Here's sulfate, H2SO4, so drop the ATE. This will be sulfuric acid. That's battery acid. By the way, acetic acid, that's the acid in vinegar. Acetic acid is a weak acid. Phosphoric acid is a weak acid. Sulfuric acid is battery acid, and it's strong. Here is bromide. So this is hydrogen bromide. This is an IDE, a binary acid. So we're going to drop the IDE, add the prefix hydro, and the suffix ic, so we have hydrobromic acid. This is nitrite, HNO2, polyatomic oxyanion. Drop the ITE, just say the anion name, nitrous acid. That's an ITE. It goes to OUS, nitrous acid. Okay? And this is the one everybody messes up. So this is hydrogen hypochlorite, if I were to try and name it as a molecule. So this is the hypochlorite anion. So you know the ITE is going to us. You've got the prefix hypo. You keep that prefix, so this becomes hypochlorous acid. It's going to take some work to learn how to name acids, but you need to do it, okay? Bases and salts. Bases. Here we go with bases. Well, bases are metal hydroxides, so substances that can react with or accept hydrogen ions. Bases increase the hydroxide ion concentration. Bases decrease the hydrogen ion concentration. We call them proton acceptors. So just like acids are proton donors, bases are proton acceptors. They decrease the concentration of hydrogen ion. Well, here's your hydrogen ion. This is your acidic solution. You pour in some base, it's going to dissociate. This is the hydroxide ion. The hydroxide ion is going to react vigorously with the hydrogen ion, and it's going to make water. So acids and bases neutralize each other. How do they neutralize each other? They get together and they make neutral water. That's what bases do. This is a major reaction, acid-base chemistry. These two guys love each other, and they're always going to get together when they can to make water. Okay? All right, salts. Salts are the ionic compounds that can be formed by replacing one or more hydrogen ions of an acid by a different positive ion. And so we talked about that just a little while ago. So if I have HCl plus sodium hydroxide, this is a strong base and a strong electrolyte. This is a strong acid, and what's going to happen is the hydrogen ion, the hydroxide ion will get together, they'll make water. That's going to be the driving force for our reaction. But what you've got is a metal cation and a nonmetal chloride anion, and so that's going to give you a salt. And there are just lots and lots of different salts. Just because this is the one you're familiar with does not mean that this is the only salt you will encounter. So here we go. Here's your base, sodium hydroxide. It dissociates in water to form sodium cation and hydroxide anion. Here's your acid. It also dissociates in water, or ionizes in water is more appropriate, into H plus and chloride ion. These are both strong base, strong acid. They're both strong electrolytes, but they react with each other to form water and a salt. This is what we call an acid-base neutralization reaction between acids and bases. Both the hydrogen ion, hydroxide ion concentration decrease. Okay, I think that's enough.